Swayam Prabha. Digital India. Educated India.
So in this lecture, we are going to see logarithmic mean temperature. You already know the definition of logarithmic mean temperature, and we have actually dealt with it when we were doing internal flows. So we are on section 4 in heat exchanger design and on slide number 54. So as we are aware, the logarithmic mean temperature difference, also known as log mean temperature difference or LMTD in short, it is used to determine the temperature driving force for heat transfer systems which involve liquid flows or fluid flows, most notably in heat exchangers. So we are aware that this LMTD gives the most appropriate temperature difference, and we will also derive it quickly again, although we had done it earlier in when we were dealing with internal flows. So what is LMTD? The LMTD is the logarithmic average of the temperature difference between the hot and the cold feeds at each end of the double pipe heat exchanger. So when you have hot and cold fluid going, entering at one end, for example in a parallel flow heat exchanger, in a counter flow heat exchanger, if you remember, the hot fluid, if it enters from the left, then the cold fluid will enter from the right hand side. So please remember those temperature profiles, qualitative temperature profiles of a parallel flow double pipe heat exchanger and a counter flow double pipe heat exchanger. So for a given heat exchanger with constant area and heat transfer, the larger the LMTD, the more heat is transferred naturally, because Q is equal to UA into delta T, and with this delta T is the appropriate delta T is the LMTD, and therefore as the LMTD increases for a given heat exchanger design, the Q will increase. The use of LMTD arises straightforwardly from the analysis of heat exchanger with constant flow rate and fluid thermal properties, and that is what we are going to do for a parallel flow heat exchanger in the next slide, slide number 56. So here you see a pipe in pipe heat exchanger, and we have qualitatively seen the way the temperature profiles of the hot fluid and the cold fluid will vary as they flow inside respectively in this heat exchanger. So what we will do now is to analyze it. We will take a small section of the heat exchanger and try to apply the energy equation under the assumptions which we have already discussed in the last lecture. So this is the hot inlet, this is the hot outlet, this is the cold inlet, and this is the cold outlet, and this derivation we are doing it for a parallel flow heat exchanger whose qualitative temperature profile is shown here. And we will take a small element wherein heat transfer is taking place from the hot fluid to the cold fluid, and naturally for this small let's say section, we can write the equation delta Q dot is equal to minus m dot Cph into dTh. The minus sign is because this is losing heat, and if you write here dTh, then naturally it will be the downstream direction minus the upstream direction, and therefore the minus sign has to come. This heat is now taken fully by the cold fluid. So you can write for the cold fluid del Q dot is equal to m dot C Cpc into dTc, where C represents the cold fluid. In this diagram, you can see that the maximum temperature difference, which is delta T1, is at the inlet of the heat exchanger, where the hot fluid is at the highest temperature and the cold fluid is at the lowest temperature. Now as it flows, naturally heat transfer takes place, the hot fluid cools down, and asymptotically speaking, if this heat exchanger is infinitely long, then at the outlet both the temperatures will be of the same magnitude, the hot and the cold side. they will merge, and then no more heat transfer will further take place. So with this energy equation, simple energy equation, under the assumptions which we have discussed, you can write dTh, or change in the small change in the temperature of the hot fluid is del Q dot up divided by m dot h into Cph, and naturally similarly dTc will be equal to del Q dot divided by m dot c into Cpc. So you can subtract the two equations and you can write the difference equation, which is noted here. So now this is from the first law of thermodynamics. Now from the transport equation we can also get the dq as follows, which we do in slide number 57. So in slide number 57 you see the dq can also be written as u into delta T, that is Th minus Tc, into dAs, that is the small temperature difference, the small area which we are focusing on. So this area also has the local temperature Th, which of course varies with location, and the local temperature Tc, which is the local temperature here of the small section which we have taken. And therefore, if you substitute this del Q dot in the energy equation, you will immediately get the logarithmic, straightforwardly you will get the logarithmic mean temperature difference definition, because here you can see that now you can write this as ln Th out minus Tc out divided by Th in minus Tc in. Now incidentally, as you can see on this figure, this Th out minus Tc out is the temperature on the right hand side, which is denoted here as delta T2. And Th in minus Tc in is the temperature difference at the inlet of the heat exchanger. So you see the delta T2 divided by delta T1 is the change in temperature at the outlet divided by change in temperature at the inlet, is equal to minus UAS when you integrate this. The inlet temperature difference divided by Q dot minus the outlet the outside temperature difference divided by Q dot. So immediately you can rearrange this equation into and compare it with Q dot is equal to UA delta T, where the delta Tm definition now is equal to delta T1 minus delta T2 is divided by ln delta T1 divided by delta T2. To take care of the minus sign, we have just reversed the term inside the natural logarithm. So you see we have again derived the logarithmic mean temperature difference as a natural outcome of applying the energy equation and the transport equation to our parallel flow heat exchanger. So moving on to slide number 58. Now this is not the arithmetic mean. You can see this has a logarithmic term at the bottom, and therefore we will see later that this is a natural let's say temperature difference, which is the actual let's say applicable difference which will give you the correct answer based on the energy equation. So moving on to slide number 58, where we will now take up the counter flow heat exchanger. Now in a counter flow heat exchanger, you remember in the diagram as seen, the delta T doesn't, or the qualitatively the temperature does not vary as we have just seen in a parallel flow, because here the hot side fluid is entering from one end of the heat exchanger here, which is the left side in this diagram, but the cold fluid enters from the right hand side. So in contrast to parallel flow heat exchanger, this configuration provides for heat transfer between hotter portions of the two fluid at one end and colder portions on the other. So the qualitative temperature profile is quite different than a parallel flow heat exchanger. Now what will happen if you make this asymptotically long? In the limiting case, the cold fluid will be heated to the inlet temperature of the hot fluid. So essentially if you make it very long, then naturally this point will shift upwards and it will eventually meet the hot fluid in an infinitely long heat exchanger. However, the outlet temperature of the cold fluid can never exceed the inlet temperature of the hot fluid. So this is also very clear that the outlet temperature of the cold fluid, which is this one, will never exceed the inlet temperature of the hot fluid. So it can asymptotically only reach it. We can derive, we can apply the energy equation to this particular counterflow also, and you will see that the expression for LMTD is more or less exactly the same. That is what is shown here. The change in temperature difference delta T, that is TH minus TC, along the length of the heat exchanger is in nowhere as large as for the inlet region of a parallel flow heat exchanger. So naturally, in the inlet side, in the parallel flow, the delta T is at the inlet, which I have circled here with a dotted ellipse. Those are pretty large, and naturally this inlet of the cold is actually on the left hand side in a parallel flow heat exchanger. So note also that the outlet temperature of the cold fluid may now exceed the outlet temperature of the hot fluid. So this is also possible in a counterflow heat exchanger. So if we do the entire derivation, which we will avoid doing here, it's a long derivation which we can do, we will see that in this case also the expression for LMTD comes out to be the same. However, the way the delta T1 and delta T2 is interpreted in the case of counterflow heat exchanger is somewhat different, in a sense that delta T1 is TH in minus TC out. So TH in minus TC out. So you again take the left hand side, the temperature difference on the left and temperature difference on the right, that remains correct or identical to the previous definition of LMTD for a parallel flow heat exchanger. However, in this case, the left hand side temperature difference represents the TH in minus the TC out, and the right hand side temperature difference includes the TH out minus TC in. So if you stick to this let's say definition of delta T1 and delta T2, then the expression for LMTD is exactly identical to what we have studied for a parallel flow heat exchanger. So moving on to slide number 60, we should also note that for a specified inlet and outlet temperatures, the delta logarithmic mean of a counter flow heat exchanger is always greater than that of a parallel flow heat exchanger. So you can also do, when you will solve the problems, you can also check this and verify because of the unique configuration where the TC in is on the right hand side and the TC out is actually on the left hand side, and therefore they are always having an LMTD which is larger. Now if you remember, this delta T can be made equal throughout the heat exchanger if the heat capacity rates are the same. So when the heat capacity rates of the two fluids are equal or identical, then naturally the LMTD will be equal to delta T1 and will be equal to delta T2, because this will become straight lines in fact, and you will have the same temperature difference right throughout the heat exchanger. So you can maintain the constant difference because of this configuration in which the hot fluid enters from here but the cold fluid is entered from the other side, and therefore as the heat exchange takes place and the fluid passes through that, you will see that LMTD can be made constant, provided of course the heat capacity rates are also identical. So moving on to the last slide now, what we have seen in this lecture is that the appropriate form of the mean temperature difference between the two fluids exchanging heat with each other in a heat exchanger is logarithmic in nature, that we have seen. It was also noted earlier also in earlier lectures. And for specified inlet and outlet temperatures, this LMTD for a counterflow heat exchanger is always greater than that of the parallel flow heat exchanger. This information will also be used later when we design heat exchangers in favor of the counterflow heat exchanger. So with this we end micro lecture 4 at slide number 61. Now, how to go about finding the LMTD for other type of other configurations? Right now, we have only done simple pipe-in-pipe heat exchanger. So, for other type of heat exchangers, how do we find the LMTD is what we will take up in the next lecture, and also we will see how the arithmetic mean temperature difference can be compared, or is it comparable with the LMTD. In the last lecture, we have seen the logarithmic mean temperature, and we have also derived the form of the logarithmic mean temperature for the two simple designs, the pipe-in-pipe heat exchanger for parallel flow and counter flow. So in this lecture, what we will do is, now we have seen several different types of heat exchangers: shell and tube heat exchangers, cross flow heat exchangers, different configurations, plate heat exchangers. So now, how do we find the logarithmic mean temperature difference? Because the complexity of the flow and geometry is quite diverse, and therefore we need to find out the appropriate correction factor or appropriate logarithmic mean temperature for such type of complex designs. So this is slide number 62, and we are moving on to slide number 63. So what is done is that we usually do what is called as application of a correction factor. So the delta T LM, that is the LMTD, which is applicable for a given geometry and given shape size of a heat exchanger, is equal to F times the LMTD of a counterflow heat exchanger. So what it essentially means is that if the same duty which you are using from a given heat exchanger was taken from a simple tube-in-tube heat exchanger or double tube heat exchanger, then what would have been the LMTD? So once you get that LMTD, the ideal LMTD or a LMTD for the ideal simple heat exchanger, parallel flow or counterflow heat exchanger, then you multiply that with a factor F, which depends on the geometry of the heat exchanger which you actually are working with. The inlet and outlet temperatures of the hot and cold fluid are given to you. So under these circumstances only you can find the LMTD. This can be this can be a black box which is your heat exchanger, and irrespective of what type of black box it is, once you know these four data points, you can find out the delta T1 and delta T2, and from there you can get the LMTD, and then you multiply it by F. So where do you get the F from? This we will see some some graphical let's say results for F, and we can pick it up from there. So I will just quickly tell you how to do that. So what we can write is that the heat transfer rate now can be written as let's say Q dot is equal to U AS F delta T into counterflow. So for an ideal counterflow heat exchanger, you first find out the LMTD and then multiply it by F. Typically all the correction factors are given in terms of counterflow heat exchanger. The LMTD counterflow, we know it is delta T1 minus delta T2 divided by ln delta T1 delta T2 divided by delta T2. Where delta T1 and delta T2 are given, it's also shown in this figure alongside. And where do you get the F from? The F is, we have to see some figures, some graphical solutions are available. So let us see them in the next slides. So we are moving on to slide number 64. So how is this data given? Okay, so this data is given. So you need to this data is given in the form of two non-dimensional quantities. Now that is the F for common cross flow and shell and tube heat exchanger configuration is given in the figures, which I will show you next, against two temperature ratios which are defined like this. So this is P is equal to small t2 minus small t1 divided by capital T1 minus small t1, and R, which is T1 minus T2, capital T1 minus capital T2 divided by small t2 minus t1, which is incidentally also equal to m dot Cp of the tube side and m dot Cp of the shell side. So since you know the temperatures, you will be able to find out P and R, and once P and R are known to you, then the F can be read directly from the figures, where just note that these 2 and 1 are representing outlet and inlet, the subscripts, and the capital T and the small t are representing the shell side and the tube side temperatures. Also remember, for all condensers and boilers, because there is no delta T in fact for the hot fluid or the cold fluid, depending on whether it is a condenser or the boiler, then F has to be taken as 1. So for all other heat exchangers which are based only on sensible heat transfer, you will use the charts. Otherwise, if one of the fluids is going through a phase change process, that is a condensing or boiling, then the F can be directly taken as 1. So let us see this graphical solution of F, the correction factor, which of course have been determined over a period of time through experimental data and results in terms of these two quantities P and R. So this is one such example here. You can see the heat exchanger, the small T1 and T2 are the tube side, the capital T1 and T2 are the shell side, and it is a 1 shell pass and 2, 4, 6, etc. any multiples of tube passes. So these tube passes can be more depending on the geometry and the availability of size and things like that, whatever is the heat exchanger design. And then you see here the definition of P is given along the x-axis, which is small t2 minus small t1 divided by capital T1 minus small t1. So you will, once you know T1, T2 and small t1, T2, you will be able to find out P. And then there are different R's which are given from ranging from 4 to 0.2 here in the decreasing order. So once you know R is also, the definition of R is also given on the chart itself, and which is also dependent, it's also a temperature ratio of the 4 temperatures which are known to you. So you know P, you know R, then you can get the value of F, and you can see the value of F ranges from 0 to 1.0. Typically the graph is truncated from 0.5 to 1, because below this it will be in any case it will be a bad heat exchanger, so which is not needed or not desirable. So this is one such graph, and in your book several such graphs are given for different configurations of heat exchangers, shell and tube heat exchangers, as well as cross flow heat exchangers. So we will see some examples on the next slide, which is slide number 66. So here you can see this is the graph which we just saw, and similar graphs for single pass cross flow with both fluid mixed or unmixed, they are given on the right hand side, and below you can have 2 shell passes with 4, 8, 12 and multiples of 4 tube passes. So this is like a combo unit in which either you have 4 or 8 or 12 passes. The first one was 2, 4 and 6 passes of the tubes. So this is the tube side, which is represented by small t's, and the shell side is represented by capital T. And in a cross flow, of course, there are possibilities of mixing of the two fluids or unmixing of the two fluids, depending on what type of the configuration. We have already seen this typically for air to air heat exchangers you may have, or air to liquid heat exchangers you may have something like that. And so whatever heat exchanger you are working with or you are trying to design, you will take the appropriate F. So with this knowledge, let us move on to slide number 67. How do you now use this particular LMTD method? So with this method, the task is to select the heat exchanger that will meet the prescribed heat transfer requirement. The procedure is as follows. There are some 5 to 6 steps. So the first thing is select the type of heat exchanger suitable for the application. Now, of course, this is not, I mean, on one side it is straightforward for experienced people, but in the initial days you may have to see several, let's say, factors which will decide that which heat exchanger is suitable. Then determine any unknown inlet or outlet temperatures and the heat transfer rate using an energy balance. So if the inlet mass flow rates are known and then the temperatures are known, you can always find out the outlet temperatures. So all these four temperatures must be known. As soon as you know the four temperatures, that is the hot inlet, hot outlet, cold inlet, cold outlet, then calculate the LMTD and the correction factor F, okay, if necessary. So this can be done, the step 2 can be done for a given, let us say, area and the given length of the heat exchanger. Then obtain, select or calculate the value of overall heat transfer coefficient. So this also you have studied, let's say, internal flows and external flows. From that knowledge you will have to get some correlation for the inside heat transfer coefficient and the outside heat transfer coefficient, and depending on what tube material you are choosing to fabricate the heat exchanger, and the thickness will come from the pressure rating of the heat exchanger. So these simple calculations have to be done so that you get the overall heat transfer coefficient U. Then calculate the heat transfer surface area which you would like, and the task is completed by selecting a heat exchanger that has a heat transfer area equal to or larger than AS. So once you have calculated how much area will be required, then you can go back to the manufacturing data of these heat exchangers and try to find out a heat exchanger which will satisfy your need. So this is how let us say the LMTD method is used, so that we can select a heat exchanger that will meet the prescribed heat transfer requirements. Now, as we were discussing before, the LMTD, of course, is the best estimate, but many times you can also use arithmetic mean, which will not give you good results. But just to compare the difference between arithmetic mean and the logarithmic mean temperature difference. So the arithmetic mean temperature difference can be evaluated with delta T1 plus delta T2 divided by 2. So this is a straightforward let's say calculation for parallel flow heat exchangers, where the delta T1 is taken for the inlet, both inlet temperatures hot and cold, and the outlet temperatures are required for calculation of the delta T2, both hot and cold. And in the counter flow, of course, you know that again you take the left hand side. So but left hand side is hot inlet and cold outlet. So this gives you delta T1, and the outlet of the heat exchanger has the hot outlet and the cold inlet, because it is a parallel flow, it's a counter flow heat exchanger. So delta T2 will be TH out minus TC in. So once you know this, you can calculate the arithmetic mean, and of course the LMTD also can be calculated for as we have defined earlier. Now naturally these are logarithmic, the differences are logarithmic in nature, their variation is logarithmic in nature. But if the net delta T is not very high, then this logarithmic curve can also be let's say substituted with a linear curve, which is the arithmetic mean actually. But as you will appreciate that as the delta T becomes larger and larger, the arithmetic mean will give you let's say wrong results. So delta T LM, the LMTD is always will always come out to be less than delta T AM, and therefore using delta T arithmetic mean instead of the LMTD will overestimate the rate of heat transfer in the heat exchange between the two fluids. So in reality, you will suffer because you will not actually get that much of heat transfer which you have estimated because of using the arithmetic mean rather than the logarithmic mean. Now when delta T1 differs from delta T2 by about not more than 40%, the error in using arithmetic mean temperature difference is about less than 1%. So that means for small changes in the temperatures, delta T1 minus delta T2, you can indeed linearize the equation and get a meaningful, reasonable result. But the error will increase to really undesirable levels when delta T1 differs from delta T2 by greater and greater amounts. So in general, it is always preferable to use LMTD and make a conservative good estimate of the net heat transfer which is desired. So we will close we will close this lecture by stating that the LMTD expression for simple parallel flow and counterflow heat exchangers can be easily derived, which we have seen. For other complex heat exchanger configuration, correction factors are available from design data sheets to determine the applicable LMTD. And the arithmetic mean temperature difference is not a good indicator and should be used only when temperature differences are small. So with this, we close this micro lecture 4A at slide number 71.